Okay, so it's a great pleasure to welcome Professor Robert Myers from the Perimeter Institute and the University of Waterloo to give the Chandrasekhar lecture today on the topic of entanglement, holography, and renormalization. So I'm going to request Anindo to introduce Professor Myers. But before that, I would just like to make some brief comments about the Chandrasekhar lectures. So the Chandrasekhar lectures are lectures delivered by eminent academicians on important new developments in their areas of specialty. The first lecture in any series is aimed at a general scientific audience, while the remaining ones are aimed at specialists. So I mean, the following 2 days there are 2 more lectures. So this the Chandrasekhar lectures is a series which is one among 3 other named lectures that we have initiated at ICTS. So the other, so the Chandrasekhar lectures is in the area of physical sciences, and then we have the Ramanujan lectures, which is in the area of mathematics, and then we have the Turing lecture series, which is in the areas of biology, computer science, and engineering also. So typically, I mean, any Chandrasekhar lectures is a set of 3 lectures, and associated with that is a discussion meeting. And right now we have a discussion meeting going on entanglement from gravity. Okay, so a few of past, I mean, recent lecturers from who have given this Chandrasekhar lectures include Anto George, Shankar Das Sharma, and Nima Arkari Hamed. So the next Chandrasekhar lecture is going to be by Senthil. Actually, it's again on entanglement, quantum entanglement. So today's lecture is by Professor Robert Myers on entanglement entanglement, holography, and renormalization. So, so I would like to request Rahul to welcome Robert by giving us memento.
Thank you very much.
Okay, so I'd now like to request Anindo to introduce.
So it gives me great pleasure to introduce Robert Myers from Perimeter Institute, Canada, whom I have known for the last 7 years. Rob is one of the leading theoretical physicists working in the area of string theory in the world. He received his PhD at Princeton University in 1986, after which he did a postdoc at the Kavli Institute for Theoretical Physics at Santa Barbara, before moving to the McGill University in 1989, where he was a professor of physics until moving as a founding member to the Perimeter Institute and the University of Waterloo in the summer of 2001. Now his 2 most famous works include discovering high-dimensional black holes with Malcolm Perry in 1986, a paper which has been extremely influential and has garnered more than 1,300 citations, and discovering the dielectric effect in the context of D-branes, which is named after him in string theory in 1999, a paper which has got more than 1,000 citations. For the past few years, he has made several important contributions in developing an understanding of the renormalization group flows and quantum entanglement in field theories, through developing intuition using what is called the ADS-CFT correspondence. We'll hear more about that in this lecture. Several of these results, in spite of their stringy origins, now are understood purely in quantum field theory language. Rob has won numerous prizes. To name a few, it includes the Herzberg Medal in 1999, the 2005 top prize in theoretical and mathematical physics, awarded by the Canadian Association of Physicists, and the Centre de... Okay, I won't attempt to pronounce that. The 2012 Watt Medal by the Canadian Association of Physicists, and Triumph for outstanding theoretical contributions to subatomic physics. He was elected as a Fellow of the Royal Society of Canada in 2006. And very interestingly, he is one of the few people to have won the first place award in the Gravity Research Foundation essay contest more than once. And past winners of this contest, which was established for the purpose of stimulating thought and encouraging work on gravitation, include Stephen Hawking and Roger Penrose. Rob was named as one of only 3 Canadian physicists on the list of the world's most influential scientific minds in 2014, the Thomson Reuters list of top 1% of researchers who wrote most cited papers in the field over the period of 2002 to 2012. On a personal note, Rob was my postdoc mentor. I have written several papers with him and is remarkably hardworking. At one point during his tenure as the interim director of the Perimeter Institute, he wanted to have some physics discussions with me at 7 a.m. To put things in context, he went to work at that point of time at 4 a.m. My extreme disgust at this proposal must have shown on my face, since after this proposal we mostly talked in the afternoons. So let's not wait much longer. Robert Myers.
Okay, thank you. Can you hear me? Is that working? Okay. It's a pleasure to be here. It's only my second time to India. The last time was 2001, so quite a while ago, but I hope that I can come and visit more often in the future. So titles are not my strength, but the title I submitted to Aninda at his persistence was New Dialogues, Entanglement, Renormalization, and in Holography. But I thought dialogues, no. How about connections? Well, that didn't sound much better. How about a new alliance? No. How about a new synthesis? Well, all of that sounds like I'm talking to a business school or something, and this is the Indian Institute of Science. So instead, I thought, new collisions in physics. That's a good physics word. So now I've got the first half of the title worked out, but unfortunately, I expect that many of you are reading the second half, and it reads something like that. So the first half of my talk will actually be just a lightning review to introduce you to these three topics. And then also the new collisions is the idea of an overlap or new convergence of ideas between these different areas. Collisions is certainly a good physics word. As the picture here conveys, it's a time of great excitement, great energy. But it's not this kind of collision that I'm talking about. It's really a collision of ideas. And so if we look back at physics in the 20th century, that was a time of grand ideas colliding on numerous different occasions, but they gave rise to new insights and new perspectives on the physical universe. And so just to press home the point, I wanted to look at the top corner here of this diagram. And so, first of all, what we have here is electromagnetism. This is something that we learn is governed by 4 basic laws, Maxwell's equations, and it tells us about various, the behavior of various different objects, magnets, circuits, radio waves. On the other hand, on the other side there, I have a different kind of physics. It's also governed by 4 laws, but the language is very, very different. And that language was developed to describe very different beasts than the ones over here. So we might ask, what do these two fields really have in common? And well, if we think a little bit, that commonality comes when we heat things up enough, sometimes they start to shine. And so in the early 20th century, what people discovered was a theoretical inconsistency between what people talked about over here and what people talked about over here on this common ground, the so-called ultraviolet catastrophe. But of course, that gave rise to a novel new set of insights, namely quantum mechanics, and that gave us a new language, a new perspective on the physical universe. And if we look around us today, it gave us insights that shape much of our modern culture. So these are the kinds of collisions that I'm talking about, perhaps not on such a grand scale as the one that I just described here. But another warning is coming from this picture here. So this is a picture taken at the 1927 Solvay conference. I said it was a conference on quantum mechanics here. It was actually called the Conference of Electrons and Photons. But the great discussions were trying to understand what this new quantum mechanics was all about, how we should really think about the probabilistic perspective that it gave us of nature. And so the question is, Does anybody in that picture look really happy? And well, some of you may have noticed that there is certainly one person here ready to party, and that was Mr. Compton, because he was about to win the Nobel Prize in a few months later. But generally, a time of collision as well as great excitement, great energy, it's a time of confusion. And so what I'm going to tell you about today is certainly a time of, from my perspective, a time of great excitement, great energy, but it's also a work in progress. It's not a finished, polished story that I'm going to tell you about, but simply some of the hints, some of the ideas that we're developing as we go along. Okay. At the end of the talk, or towards the end of the talk, I'm going to bring us back to this picture, though, and I'm really going to put it in context of the goal that, or one of the goals of string theory, which is to unify these two theories at the bottom. So on the one hand, we have quantum theory or quantum field theory, the descendant of quantum mechanics, and general relativity, our modern description of gravity. But what we would like to do is find a consistent theoretical framework that combines those two different perspectives of the physical universe in a single unified framework. But we'll see that much later. Right now, what I'd like to do is start with my tour of those three topics on the right-hand side of the transparency. So here we had the renormalization group, holography, and entanglement. As the Venn diagram shows, or what I'm trying to convey, is that those are each separate areas of study, but what we're finding are common ground between them. I've also listed a number of different topics around the outskirts of the diagram because each of these was developed in a context to explain certain sets of physics or physical phenomena in different areas. And they all developed a language that touches on many different kinds of physics. And so it may be a surprise then to see these commonalities emerging today. But we'll start at the top with renormalization, or the renormalization group. And that's actually a very simple idea that we're all probably used to. It's the idea that in many systems we have a set of microscopic constituents. However, when we assemble them together, they can merge to produce new collective effects on a macroscopic or a much larger scale. And so that's illustrated in my picture here. But if we go to Wikipedia, the font of all knowledge in the modern day, it describes the renormalization group then as a mathematical procedure by which we understand this kind of systematic development from microscopic scales to macroscopic scales. And one of the interesting features or discoveries that comes out of that is that physics at large scales really doesn't care about all of the details of the physics at short distances. And that's extremely important. That's really why physics works today. When I describe the water here, I use a few parameters, perhaps the density, the temperature, it's flowing, so that locally there may be some velocity field that I assign to the water. But I don't have to care about the positions, the orientations of all of the individual atoms in the water, or the quantum state of the nuclei, or the behavior of the gluons inside of the nuclei. We really just work with a language and a set of variables that we now call hydrodynamics. And so I've got a small cartoon here. Hopefully you've read it by now, but this is not our world. We don't have to worry about the vagaries of quantum gravity to build a better airplane. So again, the key idea was that all of the short distance physics gets packaged into a very few parameters of some effective theory. The context in which I'll be talking about it today is really in the context of quantum field theory. So there, the renormalization group emerged first out of a bunch of ad hoc tricks where people were trying to understand infinities in their equations. It was perfected with the help of condensed matter physicists. and the study of physics near phase transitions. And what we come up with is an understanding, well, it's packaged in the mathematics of the renormalization group, but here I've depicted it in this picture. So the axes here on the picture might be some parameters in my effective theory. As I integrate out some of the short distance scales, if we start here in the picture, we would flow along one of the blue lines in the direction indicated by the arrow. So we would move around according to those lines in the parameter space. Now, there's a special set of points in that flow diagram that I've marked in red, and these are the fixed points, and they play a special role because that's where the flows end or begin. And so, for example, if I'm integrating out and I sit here, my parameters stop changing. This is the end of the road, if you like, for that particular class of theories. And that, again, I'm applying this in the context of quantum field theory. That's a very special kind of quantum field theory that describes those points. And those are known as conformal field theories, or CFTs. In that case, I have a quantum field theory with a very few parameters, but they're distinguished because those parameters don't have an intrinsic scale. It doesn't matter how much more integrating out I do of physics at different scales, I sit at the same point. And so I just wanted to take the opportunity to introduce the idea of a CFT because that's something that comes up again and again later on in the talk. So that was my lightning introduction to the renormalization group. So if we move around the diagram, next we arrive at holography. Now this is a word in the common parlance or the common language, and it evokes images like that. But this isn't the holography that I'm talking about today. Holography that I want to talk about or think about is in the context of gravity. And it really came or emerged from a discovery in the early 1970s that black holes, these regions of high gravitational fields where the field strength, the gravity is so strong that classically at least, or we had thought that nothing could escape. What Stephen Hawking showed is that when we take into account quantum fluctuations, in fact, radiation is slowly leaking out of those black holes all the time. Combining his new discovery of this leakage with earlier work by Jacob Bekenstein, what people discovered is then, or what they reasoned is that the black hole has an entropy that's associated with it, even though it has a very low temperature. And more remarkably, that entropy is encoded in the geometry of the space-time. This A is the area of the event horizon, or the surface that encloses the region of no escape. I've also written all of the various fundamental constants because another important aspect of this result is that it becomes a watering hole for many different areas of physics. So if we look here, we have the speed of light that tells us about relativity. We have Boltzmann's constant that tells us about thermodynamics or perhaps statistical physics. We've got h bar from quantum theory, and then it's a gravitational system, so we have Newton's constant there. And in fact, in this formula, we see quantum and gravity next to each other. And so people like me have long been curious or studied that formula because we saw it as potentially a window into the nature of quantum gravity, this unified framework of the quantum theory and the gravitational theory. One of the things that this formula does tell us, even if we don't fully understand quantum gravity yet, is that when I combine all of these constants in nature, that it provides us with a fundamental length scale, the so-called Planck scale. So if I put the g, the h bar, and the c together in this way, I get the Planck scale, some distance squared. And so what we're really doing with this entropy is we're measuring the area of the event horizon in units of the Planck scale. Now, one of the important things, or one of the things I want to emphasize, is that this distance scale is really, really, really small. It's some 10 to the minus 35 meters. You can compare that with 10 to the minus 20 meters, which you could think of as the resolution of man's best microscope, the Large Hadron Collider in Geneva. Now, because that number is so small, that means that this entropy is going to be really, really big. And so a comparison we can make is we can look around at our local star, the sun. It's a big bag of hot gas. We think that it has a lot of entropy. It's a bag of gas that is, let me see if I can remember, approximately 700,000 kilometers in radius. The temperature varies from thousands of degrees at the surface to tens of millions of degrees in the center. And one can go through rough calculation, and one finds that the entropy of this big bag of hot gas is around 10 to the 58 times the Boltzmann's constant there. Now, on the other hand, if I take that same bag of gas and I crush it down to a ball of radius about 3 kilometers, I form a black hole. That black hole has a temperature which, according to Hawking's formulation, is only on the order of nanokelvin, and yet the entropy that I calculate with this formula here is 10 to the 77. So that's a much more impressive big number than this already big number here. So that's just to emphasize that the entropies we're talking about here are very large entropies, although they're hidden in these mysterious black holes, which apparently have very little radiation. Okay, this Boltzmann's constant, again, reminds us that the people who developed entropy, what they were interested in were things like the heat or the work losses in their steam engines. And so these ideas were originally developed in the context of thermodynamics, or thinking about various processes involving black holes, and it goes by the name black hole thermodynamics. But just as with any ordinary statistical system, or ordinary system, we believe there's also a statistical mechanical interpretation of the entropy. And so this number should be also telling us about some set of microstates, or some set of states that come together to make up that black hole. And so that's a different perspective on black holes, but that's the perspective really that goes into holography. So what holography is saying is that the horizon here is encoding information about all of these microscopic states that describe the black hole, but it's not just describing or counting those states, but holography says that there should be an effective theory that lives on that horizon, or a theory of the horizon that also includes the dynamics of those states, and so that we can talk about the evolution of the black hole solely in terms of some theory that lives on the two-dimensional horizon surrounding the black hole. Now, this was an idea, a crazy idea, that was introduced by these two very smart gentlemen down here. But it was something that really didn't take hold until much more recently. I guess I'm showing my age by saying that something 20 years ago is recent. But these ideas were pretty hand-waving until the advent of the ADS CFT correspondence, which Aninda mentioned. Now, this is going to be a simple introduction, but the way I would like you to think about the ADS CFT is that it's a dictionary that translates between two different languages. So on one side, we have the language of quantum field theory. It's not just any kind of quantum field theory, but one of these quantum field theories that has no scale. And so that's the CFTs, or the conformal field theories that I talked about before. And in particular, on this side, it's just an ordinary quantum field theory. There's no gravity anywhere in sight. So that's the first half of the dictionary. The other language on the other side is the language of gravity. In fact, I should think of it as quantum gravity coupled to a negative cosmological constant. The simplest solution of the gravitational equations in that context is called anti-de Sitter space. So that's the ADS of the ADS-CFT correspondence. And so what we have discovered or uncovered in the past decade or more is that there's a translation between this kind of language and that kind of language. And it's proven very useful because there are many problems that are difficult to calculate in this side, but simpler to calculate on that side. But also, quantum gravity is this mysterious theory that we haven't perfected yet. And so we're getting new insights from quantum field theory, which is a theory that is well established. Now, the one thing I didn't comment on here is that this language is formulated in d space-time dimensions. So, for example, we live in 4 space-time dimensions. They're the 3 spatial directions and then time. This theory on the other side, the gravity theory, is formulated in d+1 space-time dimensions. So if this was us, that would be 4, and we would be looking at a gravity theory that describes us, or could describe the same physics, in 5 dimensions. Now and hence the name holography, because of this describing physical phenomena in d+1 dimensions with a language that lives in 1 less dimension. Now, one simple question we could ask, or one might be tempted to ask, is why does this theory need an extra dimension? What does it do with the extra dimension that this theory doesn't need it for? Well, one of the things is I said that conformal field theories are special in that they don't change with energy scale. Or another way to think of it is they have excitations that are similar at all energy scales. And so what this theory is doing, the gravity theory does, is it organizes those excitations at different energy scales according to the extra radius or the extra dimension on this side. And so part of the dictionary is the idea roughly that the radius in the gravitational picture is roughly equal to an energy scale in the quantum field theory. So if I probe the physics deep in the interior of my anti-de Sitter space, what I'm doing is I'm probing the physics of very low energies in the quantum field theory. Alternatively, if I probe physics at very large radius up here, then I'm probing the physics in the quantum field theory at very short distance scales or very high energies. And so that's one of the entries in this dictionary that I'm talking about. And that's then, well, what I said is that holography organizes things by energy scales, or it geometrizes that organization. RG flows, or renormalization group, that had something to do with energy scales. And so how do I combine the idea of renormalization group and holography together in this particular framework? Well, the first thing is that in that picture that I drew with the blue lines and the red dots, I had several different CFTs, or several different red dots that were connected by these flows. So what I want is I want a theory that doesn't just describe one CFT, but I want a theory that describes several different CFTs. And so rather than coupling my gravity theory, which is given by this stuff, rather than coupling it to a constant or a fixed vacuum energy density, I couple it to a scalar field. And so if the scalar field has an interesting potential with several different critical points, then if I sit here, I'm describing one CFT. Similarly, if I sit down there, that's a different one. And over here is a third CFT. And so with this language here, or this slightly embellished gravitational theory, what I have now is a theory that has several different CFTs in the same framework. The RG flows, or the renormalization group flows, were things that took me from one CFT to another. So it's relatively straightforward then to rephrase that in this language. What I'll look for are solutions of the equations of motion, or of this theory here, which at one energy scale, or at one radius, are near this critical point, and then they'll roll down and approach this critical point at the other end, or at, say, small radius. So as I've described it here, I'm at large radius, I'm near this critical point. That's the high energy or ultraviolet end of my renormalization group flow. And then in the geometry, what happens is the scalar field rolls down and approaches this critical point at small radius, which is the low energy scales or the infrared part of the RG flow. So that's a holographic version of this, or holographic description of this picture here. Again, what we've done is we've translated the idea of a CFT to an ADS geometry or an anti-de Sitter space, and we've translated these RG flows into new geometric solutions or new geometries that interpolate between one kind of ADS space and another one at the other end. So sort of what the ADS CFT does is it takes these quantum field theory concepts and it geometrizes them or encodes them in different kinds of gravitational solutions. So that took me, well, it's covered these two circles in my Venn diagram, and I also gave you a description of one interaction point between those two ideas. This is something that was actually realized very early on, soon after the discovery of the ADS CFT. These ideas of these holographic RG flows was also discovered. So that goes back over a dozen years now. We still have to describe this corner of the diagram, the entanglement. And so that's a set of words, again, that many of us are familiar with from our quantum mechanics courses. And what we think of, or what it usually brings to mind, is the idea of the Einstein-Podolsky-Rosen paradox, or the EPR paradox. And so the idea was there was a common source here that emitted two correlated photons, and then we had our observers, Alice and Bob. And no matter how far apart Alice and Bob were, the measurements that they made on the photons were always correlated in a certain way. And so EPR, actually, or Einstein referred to this as some kind of spooky action at a distance. And EPR actually put forth this paradox, or presented it as a paradox, because they wanted to criticize quantum mechanics. They wanted to say that there was some kind of inconsistency because of this behavior. But now we know that this isn't an inconsistency, but rather it's entanglement. And entanglement is really what distinguishes the quantum world from the classical world. Or it's one of the key features that distinguishes those two kinds of physics. And so entanglement now is not shunned, but rather it's embraced in quantum information as a resource for ultra-fast communications, or ultra-secure, or rather ultra-fast computations, ultra-secure communications. My apologies. But it's also emerging as a key driver or underlying phenomena that drives various exotic phases in condensed matter or various kinds of phenomena. So people talk about quantum Hall fluids, unconventional or high TC superconductors, and more recently quantum spin fluids. Now, let's look at this in a little more detail. This is a state that's describing the polarizations of my two photons, and I said that that was entangled because of the measurements that Alice and Bob were making. One might think that, well, I can make this state even more complicated by adding other possibilities or other states, eigenstates, into them. And this must be something that's even more entangled than this one, because it just looks more complicated. However, if we look more closely, what we see is that this is actually a product state. And so there's a state here that describes the polarization, say, of Alice's photon, and a state there. And it's just a product of those two. And so whatever comes out of Bob's measurements are going to be completely uncorrelated, or they don't care what the polarization over here in Alice's experiment is. So in fact, even though we tried to make something more complicated, we ended up with something that had no entanglement. On the other hand, if I just flip the sign here of that last contribution, I get a state that looks like this, and again, it's entangled. And it's relatively easy when I just have, say, 2 spins or 2 polarizations to fool around with all possible states and decide when I have an entangled state and when I don't have an entangled state. But what we would really like is a general diagnostic that, well, that we can apply to any of these states, or even much more complicated many body states. And it would tell us that there's entanglement or there's no entanglement, and perhaps give us a measure of how much entanglement there is. So in my field, a champion in this direction recently has been a concept known as entanglement entropy. And so that's a very general diagnostic that theorists use. Basically, what we do is we divide our favorite quantum system into 2 parts, and then we use entropy as a measure of the correlation between those 2 parts. And so there's a recipe here. Take your favorite system, divide it into 2, A and B, trace out or integrate out the degrees of freedom in, say, the B subsystem. What's left over is going to be described by some density matrix. So given that density matrix, I just apply the von Neumann formula, trace rho log rho, throw in a minus sign. That gives me the entropy. And in this context, it's called the entanglement entropy. So I can apply that to that first state there. And what I find is a density matrix here with 2 eigenvalues, both a half. And so if I evaluate this formula, what I find is that there's an entanglement of log 2, or what's now known as 1 qubits worth of entanglement. I can apply that same game or that same recipe here, and what I find is the entanglement entropy is 0. And on the other hand, applying it here gives me, again, 1 qubits worth of entanglement. So that's a lightning introduction to some of the ideas that appear in the blue circle, the entanglement circle. But what I'd like to describe next is where is the common ground between the blue and the green. And perhaps it's not surprising, but there's a holographic version, or a version of entanglement entropy that appears in the ADS CFT. Now, to get there, I have to work a little bit harder. I should explain where or how I'm going to apply entanglement entropy, because in this context, I'm going to apply it to a quantum field theory again. It's not a spin system, but rather a quantum field. The first step was dividing up the system into parts. And so in this case, what we do is we just take a time slice and draw some arbitrary line that divides the time slice into 2 pieces. So there's an inside and an outside. We integrate out the degrees of freedom on the outside. That gives us a density matrix to describe the degrees of freedom on the inside. And again, we apply von Neumann's formula to get the entanglement entropy. Now that sounds pretty straightforward, but I should warn you that if you set out to carry out this exercise in your favorite field theory, I can tell you what the answer is right away. It's going to be infinity, because unfortunately, as I've described it, this calculation suffers from an ultraviolet catastrophe. Namely, if we look at the correlations between these 2 systems, in fact, there are an infinite number of very short-range correlations in the vicinity of this blue line. And so to make sense of this calculation, I have to regulate it. And what we do, or what I'll do, is I'll just introduce a short distance cutoff. So effectively, I'm just going to throw away any of the physics, any wavelengths that are shorter than delta, or any correlations on scales shorter than this scale delta. And if we regulate we redo the calculation in this regulated format, what we'll find is that the answer is given by powers of the ratio of some macroscopic scale that characterizes how big this region is over delta to various powers that are controlled by the dimension of the space-time. So again, we live in 4 space-time dimensions, and so this starts with r squared over delta squared. On the other hand, I'm a string theorist, and so for me, D is just another dial. I'm happy to consider theories in any number of dimensions. And so I encounter situations where I have more general expressions like that. Now, in fact, if we do this analysis not just for one blue surface here, but for many different blue surfaces, all within the same quantum field theory, what I'll find is that I can actually characterize this first expression in a more geometric language. Rather than just having r squared up here, what I'll find is that the leading term is actually given by the area of the blue surface that divides the two regions in my time slice. And so, in fact, each one of these terms in that expression, each one of the denominators, has an elegant geometric interpretation in terms of the geometry of my blue dividing surface in that picture up there. Now, how do we translate this, or how do we apply this idea in the context of the ADS CFT, or how do we think about holographic entanglement entropy? Well, this is the work of two gentlemen, Ryu and Takiyanagi, which they introduced in about 2006. And so I can, in the context of ADS CFT, I said I had a quantum field theory, namely this conformal field theory. And so I can draw this picture, and I can say that I'm applying that in the context of the conformal field theory of the ADS CFT correspondence. Now, to really take advantage of the correspondence, though, what I want to do is I want to translate this difficult calculation in my conformal field theory into a simpler geometric or gravitational calculation. So this picture also lives in the geometric language. In this context, this picture lives, if you like, at the boundary or near infinity in my anti-de Sitter space. And in my cartoon, this white region under here is the interior or the bulk of the ADS space-time. So what is the translation to the gravitational language? Well, what Ryu and Takiyanagi told us to do is we should consider all surfaces that are hanging down into the bulk of the ADS, but connect up at infinity to the blue line that divided the two regions in the conformal field theory. And then what I should do is I should evaluate this familiar formula, the area over 4 times Newton's constant. That gives me some number, and so I should just find the extremal value or the minimum value of this by varying the surface. And then that picks out a very special surface. It picks out a special value or a special number here, and that number is then the entanglement entropy of, well, this particular problem in the boundary conformal field theory. And one hint that this might be an entropy is that you might recognize this as a familiar formula. This was the Bekenstein-Hawking formula that gave us the entropy of the black hole horizons. Although here I'm not applying it in its standard setting. These surfaces have nothing to do with black holes. These are just arbitrary surfaces hanging down in the bulk. And a note is that, well, this was an idea I said that came out in 2006. And like all good ideas, what happened was it was ignored for a good 8 years or so. But only recently we've begun to appreciate that this idea of holographic entanglement entropy is very insightful and is giving us a new tool or an important new perspective on the ADS CFT. And Shinsei and Tadashi were actually, earlier this fall, awarded the New Horizons Prize, in part for their development of holographic entanglement entropy. Okay, so that takes us, we've gone all the way around the Venn diagram. We've looked at this intersection, but there's one intersection that's left over up here between entanglement and renormalization group. And so we might ask, what goes in there? Well, there, in fact, we can also go back to, well, 1999. There's a very short, very elegant paper written by John Preskill. And it describes, well, the title is given here, Quantum Information and Physics, Some Future Directions. So this was written at a time when quantum information was firmly established, and it looked like a new branch of computer science. Now, John was in a physics department, and I'm sure John wasn't nervous, but I think his postdocs and his students might be nervous that he was turning them into computer scientists rather than physicists. And so he wrote this paper to describe some of the areas in physics where he thought the perspective of quantum information would give us new insight or be able to help us understand the physics. And so one of those suggestions referred to something known as the Zamolodchikov C-theorem. And in particular, what this gentleman was doing was he was looking at the renormalization group flows for two-dimensional quantum field theories. And there's all sorts of interesting formulas here, and I don't expect you to pay attention to them. But the key idea was that he found an interesting function, this C function, that lived across this space, this parameter space of the couplings in his two-dimensional theories. And so with that new function, something remarkable happened. This picture here became a picture that looked more like this. So the picture of the renormalization group flows now became a landscape where the C function measures an elevation. And in particular, one of the results of Zamolodchikov was that the renormalization group always flowed downhill in this landscape. And so in particular, that tells me that there'll never be a flow that connects this critical point with that one over there, because I'll always go downhill to a certain point, but then I have to start going uphill, and the normalization group will never take me uphill to get to that point. On the other hand, I can get flows that connect others as long as I'm going down. But another corollary is a very simple idea that if I evaluate the C function at the beginning of the flow and I evaluate it at the end of the flow, it's bigger at the beginning than it is at the end. And at the critical points, it plays an important role. It's known as a central charge of the conformal field theory. And so this is saying that renormalization group flows in two dimensions join conformal field theories which obey this inequality. Now, what does that have to do with quantum information? Well, the answer actually came some 5 years after John's paper. And it was developed by, well, this gentleman and lady, Cassini and Huerta. And what they showed was that they could reformulate the proof of this inequality in terms of this tool, namely entanglement entropy. And so what they used are some basic properties of quantum field theories, of nice quantum field theories, unitarity, Lorentz invariance. And then they had one extra ingredient, which is an ingredient that entanglement entropies generally are expected to satisfy. And so it's really given by this inequality here, but it's saying that if I don't divide my system into just two pieces, but many different pieces, and I put those pieces together in different ways, then the entanglement entropies for those different pieces glued together and whatnot satisfies an inequality like that. And so this paper that these folks wrote establishes something very important about quantum field theory, but if you go to the paper, you don't find any standard quantum field theory calculations. There are no correlators, no S matrices. Rather, there's a lot of geometry, there are Lorentz transformations, and then there's this inequality. And what they do is they're able to show that, well, the entanglement entropy gives them or reproduces a C function, and that at the critical points, it reproduces the central charge, and that in an RG flow, you always satisfy this particular inequality. And so again, here's another great idea, and what happened to it? Well, we ignored it until just a couple of years ago. What we were doing instead in this direction was trying to understand, well, you know, 2 dimensions is very nice, but we live in 4 space domain dimensions, so is there an equivalent of Zamolodchikov's C-theorem in higher dimensions? And so to answer that question, one might ask, what's the role of the central charge in a conformal field theory? Well, it plays many roles, but one is something called the trace anomaly that's described by this equation here. It says that if I take the trace of the stress tensor, in a conformal field theory, the usual answer is 0. But if I take that conformal field theory and put it on some curved geometry, what I get is something that's almost, well, not quite 0. There's something here that depends on the geometry, and then a very precise coefficient, the central charge over 12. Now, I can play the same game in higher dimensions. Again, in flat space, this would be 0. If I put it on some curved manifold, well, I'm in higher dimensions. The geometry is more complicated. There are more things I can write down here. But then there's a precise coefficient attached with each one. And so instead of just one central charge, I get 3 different central charges. And one might ask, does any one of those 3 central charges satisfy this Zamolodchikov-like inequality? Well, 2 of them get ruled out very quickly, or were ruled out relatively quickly through various counterexamples or different kind of reasoning. And so we had one central charge that was left over, and it was actually John Carty, now in Oxford, well, actually retired from Oxford, but still in Oxford, who suggested that it's actually A here that satisfies an A theorem, or satisfies this inequality along RG flows. And so in this direction, there were numerous examples, numerous different calculations showing that this was true. There was even some work in the context of the ADS CFT, but then things stalled, and there wasn't much progress. And certainly no proof was found, and certainly in the ... here, there was a counterexample proposed, which seemed to indicate that no, this theorem was not going to be satisfied. But what I want to describe is that actually in the past couple of years, there's been a resurgence of interest and rapid progress. And it all started actually with some work that I did with Aninda a few years ago. What we were doing was we were looking at holographic RG flows, but in more complicated theories. So theories with more complicated gravitational couplings. And what we found was there was a certain quantity that satisfied this inequality between the high energy end and the low energy end of the RG flow. And so here's a formula that packages what's in the brackets there. You can tell that it's a gravitational formula because there's a Newton's constant. The L is telling us about the cosmological constant. And the lambda, the mu, and the alpha, which are hidden here in the F's, are telling us about various couplings in the gravitational theory. Now, the real puzzle is, though, well, this is a nice formula. It's all in terms of the gravity theory. What is it really telling us in terms of the quantum field theory, or the CFT? One of the things we were able to show was that in even dimensions, it corresponded to a very precise coefficient that appeared in the trace anomaly. And so this actually agreed with John Carty's work. His suggestion applied not just in 4 dimensions, but in any even number of dimensions. And he suggested that coefficient should be the one that has a nice RG flow, or a nice monotonicity. And so we were agreeing with John's work with our new holographic models. On the other hand, D in our calculations was an arbitrary variable, if you like, or a dial that we could tweak. And so we could study not just even dimensions, but also odd dimensions. And so we were puzzled for a while as to what this might mean in odd dimensions. But what we were able to show was, in fact, that this coefficient, this AD star, was a universal coefficient that came out of a particular calculation of entanglement entropy. And so in the case of even dimensions, it gives a new perspective on Carty's conjecture. In odd dimensions, it gives us for the first, or gave for the first time, a framework in which you could talk about a C-theorem for odd dimensional quantum field theories. And so boldly, we conjectured that this should be an inequality or a monotonicity property that didn't just apply to our holographic models, but should apply beyond holography. Now, a year later or so, some of our friends in Princeton, studying different kinds of quantum field theories, showed that in 3 dimensions, there was a particular quantity that had nothing to do with, or apparently nothing to do with entanglement entropy, that also satisfied a nice RG flow, or properties under, monotonicity properties under RG flows. And because of how they constructed the C function, it was associated with something one might think of as a free energy, and they called this the F theorem. But in fact, a month before their paper, we had actually, or I had shown with Cassini and Huerta again, that this free energy approach gave you the same quantity as our entanglement entropy approach. So in fact, this was a confluence of different ideas, and this evidence for the F theorem, or for the theorem that we had discovered in holography, was then evident, or the holographic models and these quantum field theories were giving evidence for the same particular property of RG flows in D equals 3. More excitingly yet, though, a year later, Cassini and Huerta, in a souped-up version of their two-dimensional proof, managed to use entanglement entropy and strong subadditivity and these properties to prove the F theorem. And again, recently, they were also awarded the New Horizons Prize for this work, amongst other things. I should also mention that the four-dimensional A theorem was also proved, but using other kinds of techniques, and doesn't appear to be yet related to entanglement entropy, although there is some work suggesting that one might be able to connect it to entanglement entropy in some more complicated way. So I have a few more minutes. And so we've taken this tour of the Venn diagram. We've looked at the overlaps. There's one overlap, though, that I didn't touch on, which is the one at the center here. And so to talk about that, I want to step back and I want to look at this picture. And what I described earlier was the pursuit that many of us are making to unify the quantum theory over here with the theory of gravity over here. And in fact, what we see, both of those areas in this diagram, but they're living on the outskirts. Down here we have gravity, up here we have quantum field theory. And so the renormalization group is actually part of a bigger story, the story of quantum field theory. And similarly, holography is part of the story of gravity. And so the intersection that I talked about is in part part of the story of the intersection between quantum field theory and the theory of gravity. And so it's part of this pursuit to try and find a unified framework, perhaps, in this common area. The new player in the game is this blue circle. It doesn't really seem to belong to either the gravity or the quantum field theory. Instead, I would say that it belongs, or it's more firmly set in the area of quantum information. And so the story I told you is on a smaller scale, a part of a larger collision that's going on, where what we're excited about, or what people are excited about, is that quantum information is giving us a new perspective on these two players, the quantum field theory and the quantum gravity. And in fact, it could be, or the hope is, that the perspectives and the tools of quantum information theory may prove crucial in unifying these two ideas. And so just to give you a flavor for that, already in this talk you saw hints where there were connections between entanglement and space-time. The first one being the Bekenstein-Hawking formula describing the entropy of a black hole, where I encoded that black hole entropy, or that counting of microstates, in the geometry of the space-time. Another was the appearance of an area law. That's quite an unconventional behavior for an entropy, but it's something that also appears, as well as in the horizon entropy, in the entanglement entropy. That was Raphael Sorkin's discovery. And then we also saw that this Bekenstein-Hawking formula doesn't just apply to horizons. It also applies to other kinds of surfaces, and in particular, it was being utilized in the construction of holographic entanglement entropy. And so those are part of a bigger story where our slogan now is that in some sense, space-time is entanglement, or that space-time emerges in a gravitational theory due to entanglement of the microscopic degrees of freedom. So in particular, Raphael Sorkin long ago actually introduced entanglement entropy as an explanation, or a possible explanation, of the black hole entropy. Mark van Ramsdonk has been talking in the context of holography about the connectivity of space-time requiring entanglement. I did some work recently with Eugenio Bianchi talking about entanglement in general space-times. There are ideas of representing ADS CFT or ADS space-time in terms of a tensor network which captures the entanglement structure of the underlying theory. There's a conjecture known as ER, or Einstein-Rosen equals EPR, Einstein-Podolsky-Rosen, that's been generating some interest. And then there are other ideas in ADS CFT where one can measure entropies associated with arbitrary surfaces in the bulk space-time. If I can take 2 more minutes, though, I wanted to just describe one other thing that's recently happened. And basically, this uses another tool coming from quantum information known as relative entropy. And what you can do is you can, in some sense, measure the distance between 2 states in your theory. And so it involves not just a single state, but 2 states. I'll call rho naught a reference state and rho 1 a perturbed state. And so this gives me a measure, this formula, of how far apart these 2 states are. If it really is in the context of a small perturbation of my reference state, what one can show is that what emerges from this is something that's now called the first law of entanglement entropy. It says that in going to the perturbed state, the change in the entanglement entropy is roughly equal to some energy or some quantity here. It's not quite an energy, or it's sometimes called a modular energy, but it's some quantity that refers to energy in the regions that have been perturbed. If I take that idea and I apply it in holography, what I can think is that I started with the vacuum and I excited it. I introduced certain perturbations in my ADS CFT. And this first law tells me that there's a consistency relation between data describing the energy, which is data near the boundary or near infinity, and data deep in the interior that describes the change in the entropy. Now, this is something, though, that applies for all regions. And so if I apply it many, many times, or I think of applying this first law to all possible regions of different sizes, different positions, and in different reference frames, what you find is that there's a strong consistency on the kinds of perturbations I could introduce in the space-time. In fact, they would have to satisfy a perturbed version of the Einstein equations. Now, the reason that's important is, or surprising perhaps, is that one of the things that Einstein taught us about gravity is that space-time plays 2 distinct roles. First, it's the stage on which physical phenomena take place, but it's also the agent that manifests the gravitational forces. So the dynamics of gravity is also a part of the space-time geometry. And so what we're finding here is that before I said entanglement gave rise to an emergent space-time, that was talking in the context of producing this stage. But here what I'm seeing is that entanglement also knows about the dynamics. And so here we have an entanglement version of this phenomena, or that entanglement provides both the stage and the dynamics of gravity. In any event, that brings me to the end of the talk. And the messages, or here are some messages. One is that quantum information is being brought in as a new tool. It gives us a new perspective on both quantum field theory and on gravity, but it also gives us a new perspective on the unification, this long sought after goal of theoretical physics, of these two entities. And so it could be that in 5 or 10 years, I'll come and I can tell you about a new version of quantum gravity that incorporates the perspective of quantum information, something that I might call quantum infogravity. But another thing that this dialogue or this collision is producing is it's also producing a challenge for the quantum information theorists, because the kinds of questions that we ask in these two frameworks are not the conventional questions that the quantum information theorists are used to. And so what will also come out of this collision or this dialogue is hopefully a new version of quantum information theory that's more generally adapted to the questions that we would be interested in. And so it may also be that there's a geometric or a quantum geo information theory that emerges. And so I hope I've given you a flavor for the activity, the excitement, but I also want to tell you again that this is a very much a work in progress. There are very many different avenues that are being explored and being investigated, but there are hints of something bigger coming, and so I'll close with this. And thank you for your attention.
Questions?
Sure.
You said there was a counterexample for the A theorem at some stage, but then you said...
Oh, it went away.
It went away.
It was, well, after the first paper that Anindya and I wrote, actually, some other folks in Princeton took a more careful look at the proposed counterexample, and they found that there was some assumption that had gone into it that wasn't correct.
So just out of curiosity, in condensed matter systems, sometimes the entanglement entropy is determined by making a cut in momentum space
Yes.
rather than real space. Is that something that you find useful in your thinking?
Yes. So the standard calculation that I talked about was actually motivated, the standard quantum field theory calculation that I was talking about was motivated by the idea to understand the black holes, where there's this special place in space-time. On the other hand, you can think about, entanglement between momentum modes or at different energy scales. And so this is something that in our thinking, or in the quantum field theory sort of community, has been less explored. It has been explored, but it also arises in the context of ADS-CFT, in that what I said is that radius gave us a measure of energy scales in the quantum field theory. And so a question you might ask is, if I just draw a cut or a surface at a constant radius in my ADS space, can I assign an entropy to that? And if so, what's it measuring the entanglement of? And the idea, or well, it's really taken, it's taken off in the past year or so, but what it seems you're measuring is some entanglement between low energy excitations at small r and high energy excitations or short distance excitations that are represented by large radii. So I've geometrized your cut and turned it into a spatial cut again, but it really seems to be telling us in the quantum field theory language about these entanglements between different energy scales, which is the kind of entanglement I think that you were talking about. Sure.
So you assume that the Hilbert space can be split as a tensor product of A and B. So there are some systems like gauge series in which there is no not in any obvious way a separation of gauge invariant variables between tensor in the form of a tensor product. So any sort of comments on that?
Yes. I mean, so that's actually surprisingly well known in the cadets matter community, and what they instruct us to do is just, you make your cut, and well, what I've got left over is not gauge invariant, so I have to add new degrees of freedom along the cut to sort of make it gauge invariant. And so the entanglement entropy actually captures some new degrees of freedom that we didn't normally assign to the gauge theory. That may give you a hint that, for example, in the C-theorem that I was talking about, that perhaps the entanglement entropy that I was counting or using to count degrees of freedom wasn't quite the right measure, and that we should use some other tools. And I think I'll be talking about that on Friday. So I'll just say stay tuned.
Any further questions? Okay, so just to let you know the, okay, there's one more.
So in everything that you said, I mean, though you had string theory in one corner, these ideas that you've mentioned don't seem particularly tied up with string theory. Or are they somehow subtly? I mean, apart from the ADS CFT correspondence, the ideas of holography in a more general context. So I don't see string theory here very prominently.
No, I didn't see strings anywhere in the talk either, other than I call myself a string theorist. No, it's certainly true that many of these ideas can be applied outside of string theory. It's not necessarily the sole domain of string theorists. Certainly my own thinking, though, has been shaped by a journey and being buffeted by various ideas coming from the string theory community.
So the second Chandrasekhar lecture will be tomorrow morning at 9:30 a.m. in ICTS. This is going to be one of the first technical talks. And the third one will be on Friday at 9:30 a.m. again. So let's thank Rob for a wonderful talk and wonderful lecture. And for the participants of the discussion meeting, just to remind you that there is going to be dinner from 6:45 p.m. in ICTS.